Moving on to tonight's speaker, it's my pleasure to introduce Mark, and I'm sorry, I'm going to probably butcher your last name, Subbarao. Okay, got it. Thank you. A Hillsmere resident who leads NASA's Scientific Visualization Studio, which is responsible for visualizing NASA science results for public audiences, such as us. Before joining NASA, Mark spent 18 years at the Adler Planetarium in Chicago, which Joan and I visited actually one time. We're visiting our son, where he produced planetarium shows and designed museum exhibits featuring data-driven scientific visualizations. During 2019 and 2020, Mark served as president of the International Planetarium Society, which is a big deal, by the way, where he spearheaded an initiative to help planetariums make it easier to visualize scientific data. Before that, he worked at the University of Chicago, where he was part of a team that created the largest 3D map of the universe, the Sloan Digital Sky Survey. So, Mark, take it away.
Thanks, Dennis.
Let me scoot in here. Thank you.
Yeah, so it's a real pleasure to be here. I was just telling Ryan that I was down at Kennedy Space Center this morning. We were working to 2 a.m., so I'm like really tired. I flew in this morning. But I wouldn't miss it. Yeah, so that's a little my history. My wife Amanda is the background. I live on Magnolia, but sort of went from being a research astronomer. But because when we were making this giant map of the universe, I realized, well, I know how to draw a 2D map on a piece of paper. How do you make a 3D map? And that naturally led me into computer graphics, which sort of led to this career into planetariums and data visualization. 4.5 years ago, I was able to join this group, the Scientific Visualization Studio, which was a group I had admired and used their work many years. They've been around 30 years. I think it's kind of the preeminent group doing data visualization, especially sort of like what we call cinematic scientific visualization. And I'll give you some examples of that. So here's a sort of trailer we made of sort of a year's work. And you get a sense of kind of what we mean by cinematic. So it's using the language of cinema, camera pass, lighting, whatnot, to create a sort of more immersive, engaging experience. And so we work with all of the NASA science disciplines. That's astrophysics. It's where my background is. It's planetary science. It's heliophysics. But actually, what surprises a lot of people is most of our work is actually in earth science. I won't talk about as much about that today, but at the end, I'm going to show you a little bit, and I'm actually going to invite you to, when I was down in Kennedy, we were installing an exhibit there, but we have 2 in the DC area, so I'd like to invite you to visit one of those exhibits. One of the great things about being trusted to visualize NASA science is that NASA science covers almost all science. It's amazing the sort of breadth of NASA science and the amount of, I think, for example, at the Goddard Space Flight Center, there are more Earth scientists than any institution in the world. There are more heliophysicists than any other institution in the world. These are some of these. These are the dashboards that we're building out for this exhibit. I was going to invite you to, but that was meant for a 30-foot display that is at the Smithsonian.
Are they going to be at the Smithsonian?
We have an exhibit there called the Earth Information Center.
For now?
Yep, a permanent exhibit.
At the Science Center or?
At the Natural History Museum, actually. All right, so I kind of used the cruise metaphor in the title. So this is your itinerary. We're gonna head out into the universe, talk about eclipses. Because we had a pretty big one last year. Hopefully everybody saw it. We'll touch on the moon, but I don't want to steal too much moon stuff from Ryan. And then one of the big missions for Goddard was the OSIRIS-REx mission, which actually brought back a sample from the asteroid Bennu and we're now getting great science results from that. We're going to show some visualizations we did for that, and then we'll talk about some of the fun deep space objects, neutron stars, pulsars, black holes, and then we'll come back. We'll come back to Earth, so you can go home. I don't want to leave you out there. I mean, that would be bad. All right. So we had a pretty incredible event last year, the total solar eclipse. So this is showing you a visualization of what's happening. Of course, an eclipse is a shadow, and this is one of the interesting things about this visualization is you kind of rarely see it, the system to scale. So we kind of foreshortened it there, but we'll pull back and we'll show you how that shadow is to scale. Because the moon's orbit is somewhat elliptical, sometimes we actually are a little bit beyond that shadow gets beyond the point, and that's when we have annular eclipses. We can't, for 2020 and 2023, there was an annular eclipse. But yeah, so there you get to see the whole system of scale, right? So that's the Earthing system of scale. And that's one of the things we sort of pride ourselves in trying to be very accurate. Although this is a diagram, but this is a diagram, this, hopefully, maybe you saw this map, it was all over the place last year, but this was the map our team produced of the solar eclipses. You see the annular eclipse, it's little yellow outlines to show you it's lit up. And then the total solar eclipse. So who got to see totality? Where'd you go?
Canada.
Oh, really?
Yeah.
Wow.
Clear sky.
Yeah, like everybody's saying, don't go to Canada because the weather predictions are terrible, but it was great. Anyone else make it? All right. Well, my wife made it with me. One piece of advice, like, when there's get yourself in totality. And people will see stats like, oh, it's 87%. Like, that's 80%. No, like 80% is nothing. The difference is it's that last percent that makes all the difference, being in totality. So next time you have an opportunity, whether it's here or you can travel around the world, find one almost every year, do that. Now, the special sauce, we had some special sauce in the making of the maps. It has to do with the shape of the moon's shadow. And so here's a visualization showing that. So this is the shadow for 2024 passing through. And this is an accurate calculation. So a lot of times you see these maps and you'll see an ellipse. And this is classically, it's been something that mathematicians have figured out for centuries. But Ernie Wright, who's in our group, was the first one to do this calculation correct. You can see it's not an ellipse. And he was able to do that because he was working on the Lunar Reconnaissance Orbiter, Ryan's project, we had the first 3D map of the moon. And then combining the shape of the moon and the terrain of the Earth and accurately calculate the shadow, you'll see we get this shape. But it's kind of a weird shape. It's a kind of looks like a lumpy potato. It doesn't really look like, you might imagine you're just projecting down the moon, but that's not how it works. So he did this calculation for the 2017 eclipse, but kind of kept it to himself. But when this visualization came out, wrote a paper, it was published in the Astronomical Journal. This is an example where being very careful about the visualizations actually led to an advancement in the science. That's where we were, near Indianapolis. So how does that work? Here is the moon, and the moon has some, and that's that weird shape. Like, why is this round moon producing that round shape? Well, it has to do with the little valleys on the moon. You see, they're not very big, but if I magnify those valleys so you can see them, it's the valleys that produce the shape, because that's the last time light can get through. And each of those valleys produces like a side of a polygon. And there are like 30 some of them. So I'll show you another. So these are actually visualizations that went in the Astronomical Journal, the scientific journal, to accompany the paper. So this is going to explain how that shape's created a little bit more. And imagine that we're projecting pinpoints through each of those valleys on the moon. and then it's the leftover space that creates the shell. All right, Ernie is our moon expert, so I'll show you some more of his visualization. This is a very popular one that we put out every year, and it is basically just a very accurate image of what the moon will look like every 10 minutes for all of 2025. And this is a lot of extra information there. So here you can see the Earth-Moon system, and you can see like as it gets closer, when it's closer, the moon gets bigger. If we happen to be in the full phase when it's very close, that's what we call the supermoon. That's just these two phases lining up randomly. One of the reasons you'll notice that he's labeling the craters at the limb. And the reason for that is that that's actually where you can notice them. So when you're fully illuminated, it's actually very hard to see the features, but it's this partial illumination that makes it easier to see the crater itself. Now, it isn't just the phasing of the moon. There's this libration, right? This has to do with the fact that everything's not a perfect circle. And that has allowed us to, we talk about the dark side of the moon, which is, we know is not the right term, the far side of the moon, but people say the dark side. But even in before Apollo, before we sent any spacecraft up there, we were able to see 60-some% of the moon just because of this libration.
I'm sorry, where's vibration?
It's this little wobbly motion that you see the moon making. So we can see around a little bit of the corners. And so like ancient maps, we're able to get a little bit past the half of the moon that we can see at any given time. Now, a lot of the work now is having to do with the upcoming Artemis missions, and so this was a visualization done to show potential landing sites for Artemis 3 near the South Pole. And the South Pole is a really challenging environment. One of the things that makes this challenging is lighting conditions. So when you're at the South Pole, the sun is never more than 2 degrees above the horizon. So you have cast very, very long shadows. And so there we were just letting time run and we're seeing some of these shadows. And you would have to worry about things like, like your lander is going to cast a very long shadow and it might block out, So this is a lot of work that we're doing now supporting this mission. And Ernie, who did those visualizations, is actually just down in Johnson giving lessons on lunar illumination to the astronauts, the Artemis 2 astronauts, and simulating their flight. And they were practicing like on a TV screen like this. You play what it's going to look like in their mission, and they're practicing taking photos with their cameras. It's kind of fun. Oh, let me pause before I go too far. So that's the current mission, but sometimes you can actually look at data from the past. One of the most famous images, probably the most, I think the most important photograph ever taken was the Earthrise photo on Apollo 8. One of the things we were able to do with looking at the LRO imaging was reconstruct the Apollo mission, because we actually don't know exactly what the path is like now. When we send the spacecraft, we know exactly where it went, and Apollo they didn't. But from the photographs and listening to the audio logs, we were able to reconstruct that path. And in doing so, there was actually a long-standing sort of debate about which astronaut took that photo. And Ernie's reconstruction of the path actually solved that. So this is the story of that. When I play it properly.
On December 24th, 1968, Apollo 8 astronauts Frank Borman, Jim Lovell, and Bill Anders became the first humans to orbit the moon and the first to witness the magnificent sight called Earthrise. Now we can see this historic event exactly as the astronauts saw it, thanks to data from NASA's Lunar Reconnaissance Orbiter, or LRO. LRO's superb global lunar maps, combined with the astronauts' own photographs, reveal where Apollo 8 was over the moon, and even its precise orientation in space, when the astronauts first saw the Earth rising above the moon's barren horizon. It happened a few minutes after 10:30 a.m. Houston time, as Apollo 8 was coming around from the far side of the moon for the fourth time. Mission Commander Frank Borman was in the left-hand seat, preparing to turn the spacecraft to a new orientation, according to the flight plan. Navigator Jim Lovell was in the spacecraft's lower equipment bay, about to make sightings on lunar landmarks with the onboard sextant. And Bill Anders was in the right-hand seat, observing the moon through his side window and taking pictures with a Hasselblad still camera fitted with a 250mm telephoto lens. Meanwhile, a second Hasselblad with an 80mm lens was mounted in Borman's front-facing window, the so-called rendezvous window, photographing the moon on an automatic timer, a new picture every 20 seconds. These photographs, matched with LRO's high-resolution terrain maps, show that Borman was still turning Apollo 8 when the Earth appeared. It was only because of the timing of this rotation that the Earthrise, which had happened on Apollo 8's 3 previous orbits but was unseen by the astronauts, now came into view in Bill Anders' side window. Here's what it looked like, as recreated from LRO data by Goddard's Scientific Visualization Studio. You'll hear the astronauts' voices as captured by Apollo 8's onboard tape recorder, beginning with Frank Borman announcing the start of the roll maneuver. And you'll see the rising Earth move from one window to another as Apollo 8 turns.
All right, we're gonna roll. Ready? Set. The impact crater was at just prior to the subsolar point on the south side is the floor of it. You're leaving because there is one dark hole, but I couldn't get a quick enough look at it. See if it might be anything volcanic. Oh my God, look at that picture over there. This is good coming up. Wow, that's great. Okay, I'll take that, not Jessel. Got a color film, Jim? And got a roll of color. Oh, yeah, that's great. Quick. Down here, just grab your color. And color exterior. There you go. That one? Yeah, I'm looking for one. Here. Hey, I got it right here. Let me get up. It's not clear. No, I got it right. It's very clear right here. Got it? It's still very well up here. Let me get the right thing. Calm down. Oh, that's a beautiful shot. 250 up 11. Oh, there's exclusion. I did. I picked you up. You should have got it now.
For the astronauts, seeing the Earthrise was an unexpected and electrifying experience. And one of the 3 photographs taken by Bill Anders became an iconic image of the 20th century. In 2018, the International Astronomical Union commemorated the event by naming a 25-mile diameter crater Anders Earthrise. A smaller crater was given the name 8 Homeward. Both craters are visible in the iconic Earthrise photograph. I'm Andrew Chaikin, author of A Man on the Moon.
Yeah, that's a great story. And of course, Bill Anders passed away last year. Let's go a little further out. Let's talk about this mission, the OSIRIS-REx mission, which brought back a piece of an asteroid Bennu, a very small asteroid. This is in 2020, there was the TAG event. This is a visualization showing what it would have looked like from the spacecraft if you were sitting on it as you approach that asteroid. Bumped it, TAG stands for touch and go. So booped it, grabbed some material, about a cream cheese container worth, and brought that back. Boom. And we actually have imaging of that, so you can see what the collection looked like. So here's what this is actual imaging. This is now not computer generated. And so that impact was pretty strong. Now what they've got is this is like it's a big pile of accumulated stuff, and so it just went in deeper, much deeper than they expected. And they actually had to fire the thrusters so it didn't just keep going. Went down about 60 centimeters. So here's a visualization we did.
This is Ben.
So these narrative ones I should preface before I start talking. But this is going to show you the history of that mission. It's just interesting to get a sense of some of the orbital dynamics. It's really complex orbital dynamics. So let me see. Whoops, I went too far.
This is Bennu, one of Earth's closest planetary neighbors, an asteroid roughly the height of a skyscraper, a remnant from the dawn of the solar system made of carbon-rich rocks and boulders. And since late 2018, the place that NASA's OSIRIS-REx mission has called home. When OSIRIS-REx arrived, it began wrapping Bennu in a complex web of observations, starting with a preliminary survey of its size, shape, mass, and spin. On New Year's Eve, OSIRIS-REx was captured into orbit by Bennu's minuscule gravity, making it the smallest world ever to be orbited by a spacecraft. In early 2019, it broke orbit to conduct a detailed survey. A series of sweeping passes allowed OSIRIS-REx to study geological features at different latitudes and times of day, enabling stereo imaging and landmark.
You notice it's also maneuvering so it's staying on the lit side. It's not wasting time on the other side.
Bennu at only 5 centimeters per pixel, the highest resolution of any planetary body, including Earth. On June 12th, the spacecraft entered a new orbit at an altitude of just 680 meters, setting another record and establishing a home orbit for the remainder of the mission. In September, it began reconnaissance on 4 candidate sample collection sites, potential locations on Bennu to touch down and collect a sample later in the mission. OSIRIS-REx concluded its first year at Bennu back in orbit, circling the asteroid's terminator, or boundary, between day and night. Here, outside forces acting on the spacecraft are balanced, allowing it to orbit within the same plane over time. Reconnaissance resumed in early 2020 with close flyovers of the primary sample collection site Nightingale and the backup site Osprey. In mid-April, OSIRIS-REx performed the first of 2 rehearsals prior to sample collection. It navigated to a predetermined checkpoint about 125 meters above Bennu, then descended to within 65 meters before backing away. After the checkpoint rehearsal, OSIRIS-REx flew one final reconnaissance sortie over Site Osprey. Then it made a series of high-altitude maneuvers while rebooting its onboard processor and preparing for its second rehearsal of the sample collection event. On August 11th, OSIRIS-REx departed its home orbit and made a 4-hour traverse to Bennu's northern hemisphere, retracing its earlier path. After performing the checkpoint engine burn to begin its descent, it made a second engine burn called Match Point to match Bennu's rotation before backing away at an altitude of approximately 40 meters. Now, the most crucial moment of the mission had arrived. On October 20th, 2020, at approximately 11:30 a.m. Mountain Time, the spacecraft departed orbit. A few hours before, mission controllers on Earth had sent the commands for the touch-and-go sample collection maneuver, or TAG. As they watched with anticipation, OSIRIS-REx steered itself to sample site Nightingale, maneuvering toward the small crater at the walking pace of a spider. At 4:11 p.m., the mission received confirmation. OSIRIS-REx had touched down and collected its sample. Following TAG, the spacecraft drifted to a safe distance away from Bennu. By the end of October, mission controllers determined that it had exceeded its goal of collecting 60 grams of asteroid material. They directed it to stow the sample in preparation for return to Earth. Before departing Bennu, OSIRIS-REx was given one final task. On April 7th, it flew over Site Nightingale to observe how the sample collection event had changed the surface. And with that, OSIRIS-REx had recorded its mark on Bennu and spun the last strand of its web.
Of course, it did return. I always tease the guy who wrote that script because walking space of a spider, like I've seen lots of spiders. They walk at all different speeds. But anyway, yeah. Of course, it's come back. When it came back, it was couldn't get the screws loose. Well, I spent months trying to get the screws loose. Finally, like after several months, got the screws loose. You can see a piece of this at the Smithsonian, at the Natural History Museum of the Smithsonian, if you want. Very, very dark, very, very, very black material. A lot of water, but what the interesting new results we've gotten are all the ingredients for life seem to be on these things. So they've detected 19 different amino acids in these samples, for example. All right. Let's leave the solar system. We'll go further out. Start out by showing you a visualization I did to show off a new catalog that came from one of NASA's older spacecraft, one of the sort of lesser known of the great space telescopes, which is the Fermi Gamma Ray telescope. So it's like the highest energy light, gamma rays. One of the things that high energy light does is you can see high energy things. And so these are neutron stars. Neutron star is something that's produced in a supernova explosion when a star explodes. Imagine taking the mass of the sun, or something big, usually more than the mass of the sun, actually, compressing it down to something the size of the Earth. So this huge, incredibly dense material. That's what a neutron star is. And when they spin very fast, they can produce these pulses of radio waves that we detect. That's why they're called pulsars. And they first detected with radio telescopes, so we can see them with gamma rays as well. So this is a catalog. Not all pulsars are seen in gamma rays, but a small number are. And this is show this catalog. So. Now the fun thing about this is that there are two kinds of pulsars. The millisecond pulsars, which actually imagine this star, something the mass of more than the mass of the sun, spinning, hundreds of times a second. Like that's what I'm talking about. But in many cases, they spin 1 or 2 times a second, or 3 times, and so we're actually showing the pulsing in the actual. There's very few times when, especially with something astronomical, you can show it at real speed. So I wanted to be able to show that pulsing with the actual pulsation speed. The millisecond pulsars are spinning fast because they're generally a binary system with a regular star who's feeding it mass and spinning it up. We can detect them pretty far out, so pretty far out in our galaxy. So just maybe a touch on the visualization side. So when we were doing this, the producer said he wanted it to seem like by Iron Man's helmet as he was flying through the galaxy. I'm like, are you kidding me? Like, have you looked at the credits of Marvel? Like, how many animators they have? But anyway, I watched a lot of like shots of his helmet, and that's like the kind of graphics they were trying to do. And also even the glowy lines or like the things in it. Well, if you watch Iron Man, maybe you'll see. All right, I kind of think of like neutron stars as like the most incredible object because of its insane density, but there's the like unbelievable thing beyond that. So what do you get if you that's kind of the last thing you can do. If you smush matter together closer and closer, you make a neutron star. That's a different state of matter. Basically, shoving those electrons and protons together, making one giant atom nucleus. What happens when you get too much of that material? The next thing is it collapses down to nothing at all, and that's black holes. So we celebrated NASA Black Hole Week every year. I don't know if you celebrate in your house. So these are some visualizations we produce for various black hole weeks over the year. This is a collection of black holes in the Milky Way, all the known black holes in the Milky Way. And black holes, we can really only detect, because we can't, except for the case I'm going to show you in a little bit, we can't see the black hole, but what we do is we see its companion, we see how it's moving, and we can infer the presence of a black hole. So black holes, we believe, since they're in this binary system, there's exchanging matter with that, and that's the accretion disk. So we're able to measure. These are all, we're not imaging it. We're just based on the parameters. What's the angle? What's the mass? How big we think the disk of the accretion disk is? Now, one of the things that black holes do is because of the intense gravity, they warp space and time. So that's what Einstein told us, that the way gravity works is that gravity bends space and things move through that bent space. And so you've seen that. If you've seen Interstellar, you've seen that bendy black hole, and you see the warping. There's no warping in that. We got really excited to do this because we're like going to do the gravitational lensing. But actually, at this scale, you don't see it. It's just too small. But if you have bigger black holes, you do see it.
So you get tons of data and you organize it in a way that produces these visual effects?
Yes.
And it must be something that you build up over time, like somebody did the first 20 years worth of visualization and then you add to it?
Well, in some cases, yeah. So like that's the advantage of having the people I showed in that picture, some of them had been, we just had a woman retired, who'd been with the group over 30 years, like since it started. And there's a certain amount of knowledge that comes from that. So and expertise in many, many different fields. So yeah, we just keep sort of refining based on that. So yeah, so those are like sort of artist conceptions of what the black hole's like. But we have been able to image actually 2 black holes. And how do you image? The problem with black holes is very, very small, and it's very hard to see things that are very small. But if you make a big enough telescope, so why do you make telescopes? Bigger telescopes are better, right? Everybody assumes, but why are they better? There are 2 things. People think you're like magnifying. It's not really that. There are 2 things a bigger telescope does. You collect more light if you're bigger, so you can see fainter things. Presumably things are farther away because they're fainter. But if you double the size of the telescope, the amount of detail you can see, fine detail, increases. So if you have twice as big a telescope, you can see twice as much fine detail. That little angle that you can subtend gets smaller and smaller. These things are very small. So what this was one of the most, of recent times, maybe one of the most amazing accomplishments scientifically, is the Event Horizon Telescope. It took radio telescopes from all around the world, and made a telescope that was effectively as big as the Earth by combining their light. And that was the hard part. was
They're all in
combining-
different locations, right?
Yep, all over. And that allows you to see a black hole, and suddenly it kind of looked like interstellar. The first one was a black hole at the center of a galaxy in the Virgo cluster called M87. And that was the image, which I think you probably remember seeing. And so the visualization is one where after this image was taken, all the telescopes, because you can see things changing over time. This not only on this scale, you can see the disk of material around the black hole, but at bigger scales, we see a jet coming out of the black hole. And so many, many different telescopes using wavelengths from radio waves, infrared, optical, ultraviolet, gamma rays, all observe this at the same time. And so this is what we're trying to show, the results of that simultaneous observation. But they're all observing at different scales. So we have different wavelengths and different scales. So I'm going to zoom out, and you've seen sort of the powers of 10 kind of things. So that's inspiration here. So that's 100th of a light year. And every little blue box, it might be hard to make out in the back of the room, is a factor of 10 bigger. And we're layering on images from different telescopes. So we're saying which one that is. Now we get out farther, we see the jet that's coming out of that black hole that I was mentioning. Now we went to 100th of a light year, now at 100 light years. So we've got a factor of 10,000 we've zoomed out. And each one is again another factor of, and now we can see images from Hubble, which also show that jet, the Chandra X-ray Space Telescope. And then on the very widest scales, with the poorest resolution, are the gamma ray telescopes I was mentioning gamma before. These are ground-based gamma ray telescopes. And that's Fermi telescope, who we're showing the pulsar data from. So it's a million light years across, from a million light years across to 100th of, so it's a factor of 100 million instead. All right. Since we're talking about black holes, why don't we fly into one? Some of the work that happens at Goddard is more on the computational side. And this is work by Jeremy Shipman. He actually did these visuals himself. The calculation of looking at so there's that kind of interstellar shape. What would it look like if we went through the event horizon of the black hole? See the bending that's due to the gravity. This inner ring of light is something called the photon ring. It's essentially photons orbiting around the black hole. So that really looks the stuff. All right, so one of the things you're having is time is like being distorted because of the presence of black hole. Now wavelength shift as well. That's not actually shown here. It's just not actually. right? So that's well, of course you can access that camera now. But like there's still light there. It's just that it can't get out. If you're in there, you could potentially still have something to see, which was one of the interesting points of this. Yeah, this is that photon ring. The idea is you can see like if it spirals in the light, it's kind of a 1 time, 2 times, 3 times. So don't do this on your laptop. Is the point of that. So NASA has 2 supercomputing facilities, one of which is at Goddard, the other one's at NASA Ames in Silicon Valley. And the Discover supercomputer it's actually like right next to my office, which is sometimes a little noisy. But it mostly is working on Earth system models. So doing this kind of work's pretty unusual for it.
And singularity is what? Disappearing into the
Yeah, I mean it's really a mathematical term, but it's basically where your equations break down. But we think of it as like it's that point of infinite density at the center of the black hole. So, but it's really kind of you just really can't do the math anymore. I mean, in a very naive sense, a black hole is like having everything collapse to a point. And the singularity is that point. But I mentioned that. All right, so let's come back to it as I promised, just so we can leave. Most of the work we do, I showed you space because it's a Stargazing club. Most of the work we do is actually earth science. And I mentioned that the supercomputer that did that calculation runs these Goddard Earth models called the GEOS model. So this is the highest resolution model of carbon dioxide that's ever been run. And so this was a pretty big advance. This is a model showing about 40 days in February. We're getting down 1.5 kilometer resolution. You're seeing plumes coming from individual power plants on Earth and being mixed together. And you can kind of see both the sort of local effects and also how, these things mix together and are sort of globally distributed. If we we zoom out, you see, because it's February, there was in February, like not much is growing, right, in the US, but if we look in the tropics, we actually see that pulsing is the diurnal cycle. That's the breathing of the Earth. So that's plants breathing in carbon dioxide during the day, but breathing it out at night. And you see the forest pulsing. But actually, it turns out they're actually bringing in more than they bring out. So we think that plants and also the ocean to some extent have been absorbing about half the carbon dioxide that we've been emitting. So we haven't really seen the full effects of climate change because our planet's been sort of absorbing some of it for us. Unfortunately, it can't keep doing that forever. And just a little bit more in the climate realm. I think one of the visualizations that I'm best known for is this one, which is showing data that's produced by the Goddard Institute of Space Science, GISS, who is one of the keepers of the global climate record. And so there are about a half dozen groups around the world who use all these are actual measurements on the ground from thermometers, and have been able to reconstruct the global temperature. In GISS's case, that goes back to 1880. You might have heard about them. They used to be in New York, but their lease was terminated, so they're now homeless. And in the president's budget, that institute will no longer exist, but that's not certain. You can see the pretty dramatic increase in temperatures the last few years. So all this kind of earth science stuff is, I mentioned, and just want to invite you down. We have 2 exhibits in DC. So one's at NASA headquarters, which is open Monday to Friday, 8:30 to 5:30. It's a short walk south from the mall. So you kind of head straight down from the Air and Space Museum. And then also at the National Museum of Natural History, there's a permanent exhibit where we're streaming these visualizations that are being updated every single day about all different kinds of Earth system science. Anyway, let me close there and thank you very much for coming out and for your attention.
Wow. Any other questions for? That was just amazing.
Okay, I have a question. So this may be really stupid, but when you're doing all those things on that meter, when you're doing that, are you changing by landing and taking a little cup of the stuff away and all those flying around it and all the different trajectories? Are you changing its
trajectory?
changing anything? I mean,
Yeah,
it's
yes, but not very much in that case, because it came in very, very slow. It's not a very big asteroid. But the same kind of, so the DART mission, which was a applied physics lab mission, was designed to see, can we actually change the trajectory of an asteroid?
Okay.
Because in some cases we might have to, because just to save the Earth. And they were successfully able to do that by impacting, giving it more of a stronger impact.
I'm really concerned about the defunding of all of this, and I can't imagine that we're just turning off the computers and leaving. So it's like, what is happening to try to keep it going?
Yeah, and I mean, I have to be careful here. It's hard to know, right? Because I think there's still a lot of uncertainty. I mean, and right, people are leaving. You heard about it, obviously, all the time. A lot of senior leadership is leaving, which makes some of this tough. And we don't really know what our budgets are going to be next year, but we're getting to the point where we have to make decisions about it. And it's pretty uncomfortable. Yeah, so.
Who owns that data? The GIS data? Who owns it?
Well, yeah. I mean, everything is freely available to the world. The measurements that go into it, a lot of that is actually maintained by NOAA, the historical climate records, and the NASA part is the calculation.
What about artificial intelligence? Do you see any role in analyzing the data or making things a little bit easier for you to do the more sophisticated stuff?
Oh, sure. I mean, yeah, and it's being used all the time. I'll give I'll give an example from Dennis's world of exoplanets, right? So, like the Kepler mission, which is looking for exoplanets, it studies lots of stars and looks for those light curves, and you can have regular algorithms; they're able to find most of the normal things. But with the AI, we have some examples from AI where it's being able to pull out things that are just a little weird, like for instance, the sextuple star system, which is something we thought would exist, a 6-star system. And because it's just a little bit odd, from that reason, it got missed by like the standard algorithms used to find exoplanets and that sort of. We've been using exoplanets to do things like count trees in Africa and use that to measure the amount of carbon that's stored. So, for example, there's like much more carbon stored in the desert regions than we would have thought when we actually don't count.
Okay, any other questions for Mark? How about another round of applause? Thank you.